Dear classmates, welcome back to the delay test chapter. In the previous video, we have learned a lot of path sensitization criterions. In this video, we are going to use this knowledge to help us to generate test patterns for path delay faults. So here is a motivating problem. Given this circuit, suppose that your manager asks you to generate a test pattern to detect the path delay fault B, E, G, J, K, which is highlighted in blue color. What are you going to do? So before we can propose a good algorithm, we need to answer 4 questions. Question number 1. What sensitization condition are we going to use? In this video, we are going to consider hazard-free and robust test generation. We are not going to cover non-robust test generation. And question number 2, what kind of logic system are we going to use? And how are we going to backtrace and how are we going to backtrack? So we need to answer these questions in this video. Remember that in the previous video, we used 9-value logic to show different path sensitization conditions. For a 2-input AND gate, this is a 9 by 9 truth table using the 9-value logic, where S0 and S1 represent static 0 and static 1 respectively, and R and F represent rising and falling. 0 star and 1 star represent static 0 and static 1 hazard. U1 represent a known to 1 transition. U0 is a known to 0 transition, and eventually double X is unknown to unknown. We can see that this is a huge table, which is very difficult for ATPG. There are too many states. Can we reduce this table? If we assume that we only concern hazard-free and robust test generation in this video, then actually we don't have to worry about 0 hazard and 1 hazard. As we can see from the left-hand side, this picture shows the robust sensitization condition for an AND gate. We only use U1, R, static 1, falling. So we don't actually use 0 star and 1 star. We can actually remove these 2 rows and these 2 columns from the table, so that we are left with only 7-value logic, which is much better than the 9-value logic. Now, using the 7-value logic, we have a 7 by 7 truth table for a 2-input AND gate. If we look at this table closely, we can see that actually these 2 columns can be merged together, and F and U0 columns can also be merged together. R represents a 0-1 transition for on-path signal. U1 represents X1 for off-path signal. Since a signal can be either on-path or off-path, a signal cannot be both on-path and off-path. So we cannot confuse R and U1. Similarly, F represents 10 for on-path signal, U0 represents X0 for off-path signal. We can also merge F with U0. If we merge these 2 signals, then we are left with 5-value logic, which is shown in this 5 by 5 truth table. As we can see, this 5-value logic for the AND gate. Suppose the on-path signal has a rising transition, and the off-path signal have U1. Then the output is U1, which is also a rising transition. So we can see that the 5-value logic is sufficient for us for robust test pattern generation. This is very good news. We have reduced the 9-value logic all the way to only 5-value logic. Now it's time for you to do an exercise. Using the 5-value logic, please fill in this table for OR gate and the inverter. On the side, we showed a AND gate truth table for your reference. Now please pause the video and work on this exercise. Okay, have you finished yet? For 2-input OR gate, 1 is a controlling value. If one input is static 1, then all the output will be static 1. If one input is U1, then the output would be U1, except that the side input is S1. If one input is U0, then the output will be S1 if the side input is S1, and the output will be U1 if the other input is U1. For the other case, the output will be U0 and the XX. Have you got it correctly? Now we can use 5-value logic to generate hazard-free and robust test patterns. A 5-value test pattern generation was proposed by Lin in 1987. Actually, generate test pattern for PassDelay 4 is similar to test generation for single stack 4, except there are two differences. First, X-path selection is actually not needed for PassDelay 4, since the path is already decided by the PassDelay 4. So in this sense, PDF test generation is simpler than single stack 4 test generation. Number 2, there are actually two different zeros and two different ones for PassDelay 4. In the 5-value logic, we have U0 and S0. We have U1 and S1. This is different from single stack 4 test generation, where we have only a 0 and a 1. So in this sense, PassDelay 4 test generation is more complicated than single stack 4 test generation. So how are we going to backtrace if we have two different zeros and two different ones? The rule is very simple. If our objective is U0, then we simply backtrace U0. If our objective is static 0, then we backtrace static 0. This is pretty intuitive. So we can distinguish between U0 and S0. However, we need to decide whether we have achieved our objective using the covering tree. We say that U0 covers S0, which means that it is okay if our objective is U0 and we simulate the value to obtain a static 0. However, it is a conflict if our objective is S0 but our simulated value is U0. Similarly, U1 also covers S1 and the double X covers both U1 and U0. So let's see an example to generate hazard-free test patterns. Let's use a pattern-like algorithm as an example. Suppose we want to generate a hazard-free test pattern for the PassDelay 4 PEGJK, which is highlighted in blue color. At the starting point, we assign primary input B to BF, which is U0 in 5-value logic. And then we want a hazard-free sensitization through this OR gate. So we want the side input C to be static 0. So we assign C to be static 0. And then we perform a forward simulation. So E, G, and the Q are both U0. After the inverter, J is U1. Now we want a hazard-free sensitization through this OR gate. So we would like a static 0 on the side input H. So we backtrace all the way to input A and we assign A to be S0. And we perform simulation and eventually the rising transition U1 reach primary output K. So the test is successfully generated. A, B, C are static 0, U0, and the static 0. So vector 1 is 0, 1, 0, and test vector 2 is 0, 0, 0. Okay, now let's generate a robust test pattern for the same PassDelay 4 PEGJK, which is highlighted in blue. At the starting point B again, we assign B to be U0. Now we want a robust sensitization through this OR gate. Since 0 is a non-controlling value, we don't require a static 0. We can require a U0 on the off-path signal. So we can assign C to be U0. On this 5-value table, we can see that if one side input is U0 and the on-path signal is U0, the output would be U0. So now we have U0 for E, U1 for J. Now we want a robust sensitization through this OR gate. Since 1 is a controlling value, so the off-path signal must be static 0. So our objective is static 0. We backtrace all the way to primary input A. We assign A to be static 0. And we perform a simulation. Now H is static 0 and K is U1. The rising transition has reached primary output K. So we generate a test pattern which is S0, U0, U0. This is a robust test pattern because all the gates on this path are robustly sensitized. Now it's time for you to do an exercise. Consider a PassDelay 4 DEGJK, which is highlighted in blue in this figure. Please generate a robust test pattern for this PassDelay 4. On the side, we show a 5-value logic table for 2-input NAND gate for your reference. Now please pause the video and work on this problem. Okay, have you finished yet? Here are the answers. As starting point, we assign D to be U0, which is a falling transition. If we want a robust sensitization through this NAND gate, since 0 is a controlling value for the NAND gate, the side input must be static 1. And then we want to sensitize through this NAND gate. Since 1 is non-controlling, so the side input H can be U1. And we want to sensitize through this NAND gate, so we backtrace to B and we assign B to be static 0. In this way, we can sensitize this PassDelay 4 all the way to output K. Every gate on this path is robustly sensitized. So this is a robust test. Have you got it correctly? In the test generation process, sometimes we make mistakes. If we make mistake, then we would need to backtrack. In the following slide, we show some examples of backtrack. Now consider this circuit. We will try to generate a robust test pattern for the PassDelay 4 BMNL, which is highlighted in blue. At the starting point, we assign B to be U1 because 1 is a non-controlling value for this AND gate. So our objective value for the side input F can be U1. Now we have two choices to make. We can either backtrace to C or D. Let's say we choose C first and we backtrace the same type of value as our objective. So we would assign C to be U0. Now we perform a simulation and I is U0. But this would block our PassDelay 4 propagation to the primary output. So this was a mistake. We need to backtrack. In Lin's paper, they propose that we backtrack to the same type of value. That means we backtrack an U0 to U1. We don't backtrack it to S1 or S0. Similarly, we backtrack S0 to S1. We don't backtrack it to U0 or U1. This rule is to keep our decision tree always 2 branches for each node. Now we backtrack the value of C. We assign it to be U1. And our objective on F is not still achieved. So we would backtrace again. This time we backtrace to D and we assign D to be U0. This can achieve our goal. And now we would like to robustly sensitize this path through the NAND gate. Because 1 is non-controlling value, so our objective is I equal to U1. So we backtrace to A and we'll assign A to be U1, and then we successfully propagate the fault to the output. We successfully generated a robust test pattern for this PassDelay 4. But in reality, there are many PassDelay 4 that cannot be robustly tested. Now let's generate a robust test for a PassDelay 4 BEQHK, which is highlighted in blue in the circuit. At the starting point, we assign B to be U1 and if we want to robustly sensitize through this OR gate, we can assign C to be static 0. And we can perform simulation. So Q is U1 and J is U0. Now we want to robustly sensitize through this AND gate. So we backtrace to A and assign A to be U1. Now we run a simulation and we would like to robustly sensitize through this OR gate. Because 1 is a controlling value for the OR gate. So we would like the sine input J to be static 0. However, our simulated value is U0, which is a conflict. As we mentioned earlier, in this covering tree, U0 covers S0, but S0 does not cover U0. That means if our objective value is S0, but our simulated value is U0, this is a conflict. So we need to backtrack. Our last decision, we will backtrack to U0, but this does not help. And we backtrack C to S1, this does not help either. So our test generation failed. That means this PassDelay 4 is robustly untestable. So what should we do to the robustly untestable PassDelay 4? Maybe we can downgrade our requirement and generate non-robust tests. Consider the same circuit and our PassDelay 4, PEGJK. Now let's generate a non-robust test pattern. At the starting point, we assign B to be U0. And if we want to non-robustly sensitize through this OR gate, the off path signal can be U0. And we run a simulation, and the J is U1, H is U0. And then we can non-robustly sensitize this transition to the output. So we successfully generate the non-robust test for this PassDelay 4. The pattern is double X, U0, and U0. That means in the first test pattern, we have unknown, 1 unknown. In the second pattern, it is still unknown, 0, 0. This is a non-robust test for this PassDelay 4. Please note that, generally speaking, 5-value logic is not sufficient to generate non-robust delay tests. Please see our FFT for more details. Now, let's make a summary about our old friend, the PassDelay 4, PEGJK. Totally, we generated 8 test patterns to detect this PassDelay 4, out of which 6 of them are non-robust tests. These 6 tests are listed here. Only 2 out of the 8 patterns are robust tests, out of which only 1 of them is a hazard-free test. From this result, we can see that the majority of the test patterns are actually non-robust tests. Only a small portion is robust test, and the hazard-free test is very, very few. Okay, here is our conclusion of this video. We have shown that we can use 5-value logic to generate hazard-free or robust test patterns. There are 2 types of 0 and 2 types of 1. and double X in 5-value logic. In the covering tree, we say that U0 covers S0, but not vice versa. When we do a backtrace or backtrack, we always backtrace the same type of zeros or ones. For example, we backtrace U0 if our objective is U0. We backtrack to U1 if our original value is U0. In reality, many PassDelay 4 are robustly untestable. Even if it is testable, there are many more non-robust tests than robust tests. Finally, it's time for FFT. In our video, we have mentioned that 5-value logic is actually not sufficient to generate non-robust tests. So please explain what is the reason. Here is a hint. As we can see, the output K can be either a rising transition or a static one hazard. So please use this example to answer this FFT. Thank you for watching.